Welcome back to Data Explained. I'm episode 11, and today we're tackling one of the most fundamental ideas in databases, transactions. At its core, a transaction is about two things: making sure a group of writes either all succeed or all fail, and keeping things sane when multiple users hit the same data at once. We'll walk through begin, commit, and rollback, then get into locking and isolation levels, the part that, honestly, trips up just about every developer at some point. So let's ground this in two scenarios you've probably seen. You transfer €100, the database subtracts from account A, then the server crashes before it ever adds to account B. The money just vanished. Or two users hit book on the last seat at exactly the same instant, and somehow both walk away with a confirmation. That's what transactions are designed to prevent. They group your steps into one all-or-nothing unit, and together with locking and isolation, they make sure concurrent work stays safe. All steps or none, safely concurrent. So here's the working definition. In one sentence, a transaction is a group of operations that all succeed or all fail together. And isolation controls what concurrent transactions are allowed to see. Three ideas to anchor on. 1. It's a single unit, all or nothing. 2. Locks are what keep concurrent writes from colliding. And 3. Isolation is really a question about visibility. What does one transaction see while another is still in flight? We'll unpack each of those next. Let's start with the mechanics. You open a transaction with begin, run your statements, and then either commit to make everything permanent or roll back to throw it all away. Take the classic example. Moving €100 from account A to account B. That's two updates, one debit, one credit. Wrap them in begin and commit, and the database guarantees you never end up with money subtracted but not added. It's both or neither. And that all or nothing guarantee has a name. It's the A in acid atomicity. If you remember the acid episode, transactions are how databases deliver all four guarantees: atomicity, consistency, isolation, and durability. In this video, we're zooming in on two of them: atomicity, which we just saw with begin and commit, and isolation, which handles concurrent transactions. Those two are the tricky pair that trip up most developers. So let's see what isolation actually protects us from. Picture two users hitting buy on the very last ticket at the exact same instant. User A reads the inventory, jiao, one left, and books it. But user B, a millisecond later, reads the same value before A's write has landed. So B also sees one left and books it too. Both walk away thinking they got the seat, but they booked the same one. That's a classic race condition, and it's exactly what locking and isolation levels are designed to prevent. The fix for that race is locking, and the database's way of saying, "I'm using this row, wait your turn." Once user A's transaction touches the inventory row, user B has to queue up. By the time B gets to read, A has committed, the count is 0, and B is correctly refused. There are flavors of this. A shared lock lets many readers coexist. An exclusive lock gives one writer the floor while everyone else waits. And a deadlock is when two transactions block each other, at which point the database picks one and kills it. Locking prevents some collisions, but not all of them. And that brings us to the three classic anomalies you'll see when isolation is too loose. A dirty read is when you read data another transaction hasn't committed yet, so if they roll back, you've been lied to. A non-repeatable read is when the same row gives you different answers within one transaction because someone committed an update in between. And a phantom read is subtler. You rerun the same query, and suddenly new rows have appeared because someone inserted matching data while you weren't looking. The SQL standard gives us 4 isolation levels, and they form a clean ladder. Each rung blocks one more anomaly. Read uncommitted lets everything through. Read committed shuts the door on dirty reads. Repeatable RUD also pins your rows so they can't change mid-transaction. And serializable goes all the way, behaving as if transactions ran one after another. The trade-off is real, though. Postgres defaults to read committed for a reason, because serializable is the safest, but pays for that safety in throughput. And that trade-off is really the whole story of isolation levels. Crank it up and you get fewer anomalies and stronger guarantees, but you pay for it with more locking, more waiting, and yes, more deadlocks. Dial it down and you get concurrency and speed, but you're quietly accepting that some anomalies will slip through. That's fine for a dashboard query, but it's the kind of choice that can cost you real money when you're moving funds or decrementing inventory. So when collisions do happen, the database basically has two philosophies for dealing with them. Pessimistic locking assumes a fight is coming. It grabs the row up front, makes everyone else wait, and trades throughput for safety. Optimistic locking bets the other way. Just do the work. And at commit time, check whether a version number changed. If it did, retry. Lock first and work second versus work first and verify at commit. Same goal. Very different temperament. Before we go deeper, let's clear out 3 myths that keep showing up. First, transactions aren't just for banking. Any multi-step write benefits, from signups to orders to inventory updates. Anywhere a half-finished change would leave garbage behind. Second, cranking everything to serializable isn't a virtue. It's the safest level, but also the slowest. And most apps run perfectly well on read committed. And third, locks aren't the enemy. They're how correctness happens. The real fix is keeping transactions short and picking the right isolation level, not pretending locks don't exist. Which leads us nicely into a cheat sheet of habits worth adopting. Keep your transactions short, wrap related writes into a single unit, match the isolation level to the actual risk, and treat deadlocks as a normal outcome you retry in code, not an exception you swallow. On the flip side, avoid the classics, transactions that hold locks forever, blanket serializable just to feel safe, waiting on user input mid-transaction, and ignoring deadlock errors when they fire. Before we go deeper, let's lock in the vocabulary you'll keep hearing. Commit saves all your changes. Rollback undoes them. And a lock is how a transaction reserves a row so nobody else can touch it. A deadlock is 2 transactions stuck waiting on each other. The isolation level controls what other sessions are allowed to see mid-flight, and MVCC is the trick of keeping multiple row versions so readers never have to block writers. So let's pull the main threads together. A transaction is all or nothing. Begin, commit, rollback. And that's how databases give you the A in ACID atomicity. Locks are what serialize collisions when 2 sessions reach for the same row, and isolation levels are the dial you turn to trade safety against raw speed. The practical rule of thumb: match the isolation level to the actual risk, and keep your transactions short so the locks you hold don't become everyone else's problem. If you take away just one mental model from this whole episode, make it this one. A transaction is a sealed envelope. Everything you put inside either gets delivered together or nothing does. And isolation is simply how much one open envelope is allowed to peek at another. Tighter seals mean safer data, but slower throughput. Without that envelope, half-writes and collisions quietly corrupt your state. With it, you get all or nothing, and collisions are ordered instead of chaotic. And once that envelope clicks into place, you'll notice transactions quietly show up everywhere else in the data series. ACID isn't a separate topic. Transactions are literally how ACID gets delivered. Replication is about making sure those commits land durably on every replica. Sharding is where it gets painful, because a transaction spanning shards is one of the hardest problems in distributed systems. And idempotency is the natural partner for retries when a commit's outcome is uncertain. Get this one right. And the hardest part of working with real, concurrent data is genuinely behind you. If you want to keep pulling on this thread, the Data Explained series has you covered. ACID, SQL versus NoSQL, indexes, sharding, replication, caching, queues, rate limiting, idempotency, SAP, and of course, transactions and locking, all sitting alongside each other so you can see how the pieces connect. And when you're ready to go properly hands-on with the database itself, the Dargslan PostgreSQL course takes you from everyday queries all the way through to hardening over at dargslan.com/courses. Before we wrap, a quick question back to you. Have you ever been bitten by a race condition in production? Maybe a double-booked seat, a card charged twice, inventory that quietly went negative. I'd love to hear what the bug actually turned out to be and whether isolation levels finally clicked into place once you'd lived through it. Drop it in the comments. Those war stories are how the rest of us learn. And that's transactions and isolation in a nutshell. The quiet machinery that keeps your data honest when writes get interrupted and when users collide. If you want to go deeper, from MVCC internals to tuning isolation in real workloads, the full Dargslan PostgreSQL course over at dargslan.com picks up right where this episode leaves off. Hit subscribe, and I'll see you in the next one.